Let's recall in the elliptic PDE chapter, you have this scenario where you have the boundary condition around the plate and you are going to find the steady state temperature at this 9 point. We have success to obtain the numerical modeling by using the finite difference method to be this answer. Then, by applying this equation, we can form 9 equations from this 9 point. For example, at this point, let's have the x direction to be your I and the y direction to be your j. So at this point, your I is equal to 1 and your j is equal to 1. Let's substitute inside this equation. So for this element, you have 4t11, which is this. So for this element, you have 1, 0. This element, 1, 2. Then for this element, you have 0, 1 and 2, 1. So we can substitute the information for this temperature. And here we have T12, so we don't know this temperature, we just remain. And here we have T21, so this temperature we don't know, will remain also. So T01 refer to this temperature. So at this temperature, it will be equal to 75. So we can substitute 75 here. And then at this temperature, so the temperature is T10, where it's equal to 0. So this can be cancelled. Let's move 75 to the right hand side, then you obtain negative 75 and multiply both sides with negative 1. Then you obtain negative, negative, positive, positive. So you check it and this should be positive for T11 and you have negative T21 here and negative T12 here equal to 75. So you should obtain this equation. From this point, you success to form the first equation and we can write it into matrix format. If you continue to find the temperature at these 3 points, you obtain T11, T21 and T31, which is these 3, and then you continue for this row, you obtain T12, T22 and T32, which is these 3, and for this one you obtain the last temperature here. So for the first equation, we can write in this row where you have 4 multiplied with your T11 minus 1 multiplied with T21, 0 multiplied with T31, you still get 0, and lastly negative 1 multiplied with T12, which is this. So the rest is 0, so you obtain 0 here, and then on the right hand side you have 75. If you continue to find the temperature equation at this point, then you should be able to obtain this multiplied with this column equal to 0. So for this point, you obtain the third row multiplied with the column here equal to 50. So at this point, you obtain the fourth row multiplied with the column here equal to 75. And if you continue, then you should get the remaining equation. We can find the temperature by using the Gaussian elimination and also the LU decomposition method. However, these methods are much inefficient because we are storing the 0 at many points. These 0 numbers are not useful in the calculation, therefore we waste a lot of computer memory. Also, when we perform the Gaussian elimination or the LU decomposition method, we need to perform the forward elimination at this element. We have to make this element become 0. For example, to make the first column here become 0, we perform the forward elimination. And you see, to make the second element here 0, we use this equation. The forward elimination continue to make this element become 0 by using this equation. Continue with this element by using this equation to make it 0. Continue with the rest. We have this equation. You may wonder why we still need to perform the forward elimination to make it 0. This step is not necessary because the elements already in the 0 answer. Therefore, we are saying that performing the forward elimination at the 0 element is not necessary and it is waste of the computational time. These two factors makes the Gaussian elimination and LU method to become inefficient. Therefore, to solve the inverse problem that involve band matrix, we do not recommend these two methods. In fact, we can use the Gauss-Seidel method to solve the inverse problem that involve the band matrix. In this case, you have AT equal to B and your A matrix is a band matrix. And you see a lot of 0 here and here, which make the Gaussian elimination and LU decomposition to be inefficient. We can convert the matrix format into the Gauss-Seidel format by taking the T11 from the first equation. From the first equation, form the equation in this manner where you have T11 on your left hand side. And you continue for the second equation here where you form the equation by taking the T21 at your left hand side. And you continue with the third equation by taking T31 on your left hand side. Fourth equation, T12 at the left hand side, and so on. For the Gauss-Seidel method, if you look at the equation, we do not store the 0 and we do not need to perform the forward elimination on the 0 element. Therefore, Gauss-Seidel method is more efficient compared to the GE and LU method. If you recall the elliptic PDE chapter, we are using the Gauss-Seidel method to solve this problem. At 0 iteration or no iteration, we let the Tij equal to 0 at all the points. For all these 9 points, so initially the temperature is 0. Then at first iteration, we apply the equation, and for example, to find the T11, we substitute this assumption inside the formula. So T12, T21, at these 2 points, we present to these 2 temperature, and we substitute it to be 0. T01, T10 is these 2 temperature, which is located at these 2 points. Therefore, we substitute 75 and 0 inside. So 75 divided by 4, you should be able to obtain your temperature at T11 here equal to 18.75. Please correct this typo, so it should be 3 for your I and J. So because you have 1, 2, 3 for your I and then 1, 2, 3 for your J. So by using the same method, you can find the temperature at other points, and then you proceed for the over relaxation. So this is the formula. Lambda can be chosen from 1 to 2, and if you choose a suitable lambda, then less iteration is needed to achieve an accurate solution. In this case, we choose the lambda to be 1.5, and to find the T11, you have to substitute 1.5 inside the formula, and then your temperature 11 new means the temperature that you obtained here, which is equal to 18.75, and then temperature 110 is the temperature that you assume in the 0 iteration here, which is equal to 0. Therefore, we can substitute here equal to 0. So after you compute this, you obtain your T11 to be 28. So this is the answer at T11. So if you repeat the same procedure for the other temperature, then this should be the result. If you set the stopping criteria equal to 1%, so when your approximate percent relative error less than 1% at all the 9 points here, then you should able to obtain the answer at 9 iterations to be this. In order to check the accuracy for this temperature that you obtain, you can substitute inside the left hand side function here and multiply with this matrix. So the left hand side result should be equal to the right hand side. If they are equal, then we say this answer is correct.